Good afternoon, everyone. First of all, I thank the organizers, especially Professor Abhishek Dhar, for inviting me to this very nice program on quantum trajectories. So today I'll be talking mainly on our recent result on Doppler-Enhanced Quantum Magnetometry with Rydberg atoms. Here's the plan of the talk. First, I'll give an introduction to quantum technologies with ultra-cold Rydberg atoms, why working with Rydberg atoms is so promising. And then I'll talk about transition frequency measurement of highly excited Rydberg states, which actually forms the background for explaining our result on Doppler-enhanced quantum magnetometry. And then I'll talk in details about our experiments and measurement on Doppler-enhanced quantum magnetometry with Rydberg atoms. Then I'll move over to discuss our observation of Rydberg excitation in cold atoms and the measurements we have done on that. And finally, I'll give a future perspective on scalable quantum network and quantum sensing with tweezer arrays of individual Rydberg atoms. So Rydberg atoms are giant superatoms where the electron is excited to very highly excited Rydberg state with very high principal quantum number. And so they are essentially the giants of the atomic world. So Rydberg atoms were discovered by Swedish physicist Johannes Rydberg. He found an empirical formula linking the various wavelengths of the spectral lines observed in alkali atoms. And this is the energy of the Rydberg atoms, where R(y) is the Rydberg constant, and N is the principal quantum number, which characterizes the state at which the electron is excited. And delta is the quantum defect, which characterizes the deviation of the Rydberg atoms from hydrogen-like behavior because of the incomplete screening of the inner electron core. And so Rydberg atoms, after it was discovered, it played an important role in the birth of quantum mechanics. So Rydberg atoms, because of its very highly excited electron, it imparts a lot of exotic properties to the Rydberg atoms, which makes it very interesting for various regimes of quantum technology. For example, the radius is very large. The size goes as n square, which n, where n is the principal quantum number, and this gives rise to giant Rydberg atoms, which is very much ideal for exploring mesoscopic quantum regime because of its large size. And the radiative lifetime goes as n cube, which gives long coherence time to Rydberg atoms, which is also very useful for quantum technology applications. The polarizability of the Rydberg atoms, which is the sensitivity to external DC or AC electric fields, is also very large, which goes as n to the power 7. So the Rydberg atoms is extremely sensitive to very small electric fields, which makes it an excellent quantum sensor, and also it's very useful for metrology applications. Another important property of Rydberg atoms is that it has very strong interatomic interaction. So which the dipole-dipole interaction goes as n to the power 4, and the van der Waals interaction goes as n to the power 11. So you can see there's a very strong interatomic interaction in Rydberg atoms, which makes it a very promising platform for various regimes of quantum technology. For example, we can do quantum entanglement using Rydberg blockade, which I'll explain in a few in the next slide, which makes it promising for realizing quantum gates for quantum computation. Also, quantum simulation of condensed matter systems can be done because of the very strong long-range interaction. And also, it's very useful for quantum communication because Rydberg atoms can be used as a very deterministic single photon source. So why Rydberg atoms is so promising for quantum computing? Because of at the heart of this promising application of Rydberg atoms is what is called a Rydberg blockade. Now, if you have one atom in the Rydberg state, And because of the very strong van der Waals interaction, if you have another atom coming close to the Rydberg state, if you have one atom excited to the Rydberg state with a laser, the same laser cannot excite the other atom to the Rydberg state because of the energy level shift due to the strong van der Waals interaction. So either this atom will be excited to the Rydberg state and the other one will be blocked, or vice versa. So this is a correlation which is formed, which leads to quantum entanglement of these two Rydberg atoms. So this was the introduction to Rydberg atoms. So now I go to the phenomena which we have used to do the measurements of Doppler-Enhanced Quantum Magnetometry. So before I go into that, I would like to introduce a very interesting quantum optics phenomena called electromagnetically induced transparency. And we have used Rydberg electromagnetically induced transparency to do the measurements I'll be talking about. So electromagnetically induced transparencies are generally observed in three-level closed systems. So there can be various kinds of three-level system. For example, you can have a V type of system with one ground state and two excited state, where two transitions are dipole allowed and the third is dipole forbidden. And we can have a lambda type of system where we have one excited state and two ground state with again two dipole allowed transition and one dipole forbidden. And the third kind is a ladder type of system where we have three state, one in above another in energy. And so we have two dipole allowed transition and the third is dipole forbidden. So for our measurement, we have taken a ladder kind of three-level system, which I'll discuss in a few slides from now. And so here, if we have just this two-level system and we scan the frequency of this laser across the resonance, so we'll get an absorption profile, which you can see with this dashed profile. So which is the absorption profile as you scan the frequency across the resonance. But if we have this three-level system and there's a two-photon resonance which is satisfied, then you have the destructive quantum interference of the transition probabilities of these two transitions, and this leads to complete cancellation of absorption, and we get a transparency or a complete transmission. So this is what is called electromagnetically induced transparency. And it has a lot of applications like in slowing of light, because here you can see as you have this electromagnetically induced transparency, so this dashed line corresponds to the absorption profile without the third laser, the second laser. But if you have a electromagnetically induced transparency, there's a very sharp increase in the refractive index or the real part of the susceptibility. So this property of EIT that leads to slowing of light, or we can have quantum memory, and this also has applications in atomic clocks and as well as quantum information processing. So this is our setup for observing the Rydberg electromagnetically induced transparency. So as I had mentioned, we have chosen the ladder type of system because we have Rydberg atoms in a very highly excited state. So we have two transitions. One is we use a probe laser to excite the atoms from the ground state to the first intermediate state, which is at 780 nanometer. And we use a coupling laser, which is at 480 nanometer, to excite the atoms from the intermediate state to very highly excited Rydberg state. And these lasers are completely tunable. We can access any principal quantum number of the Rydberg state. When we have just this laser, we can have an absorption profile. But as we have these two lasers, we have the Rydberg EIT, and we get a Rydberg electromagnetically induced transparency signal. So here you can see our measured Rydberg EIT signal. We have a sharp, so this is the absorption profile. And we have a Rydberg EIT signal. Here you can see that. So this is the absorption which is plotted, or the transmission if you just flip it. And you can see a big peak in the transmission where the Rydberg EIT condition is satisfied. Now here you can see that if we subtract this Doppler broadened profile without the EIT signal, from this signal we can have a signal with a flat background. So this is a Rydberg EIT signal, and this of course is signals with lock-in detection. Now when we had started our experiment, we wanted to go to very highly excited Rydberg state, but at the time in the literature, the transition frequencies to go to very highly excited states were available only till n equal to 55. So we decided that the best way to get those frequencies is to measure them ourselves. So we measured the transition frequencies all the way to 125. So we measured the transition frequencies to ns half, nd 3 by 2, and nd 5 by 2. So here you can see the signals are from all the Rydberg EIT signals all the way to n equal to 125. And so we also had measured the fine structure splitting of D 3 by 2 and D 5 by 2 with high accuracy. And most of our accuracy of our transition frequency measurements were within 1 megahertz. And so for very highly excited Rydberg state, our accuracy was around 2 megahertz. So here you can see, as we go to higher and higher Rydberg states, the difference between in the fine structure splitting becomes lower and lower, and it increasingly becomes very difficult to resolve. So here you can see the data points for our measurement, and which we had fitted with a theoretical prediction. And so here you can see these are data points, but very, very close together, because as I had said that as we go to higher and higher Rydberg states, the level spacing becomes smaller and smaller. So it's very difficult to resolve these data from one another. So we had fitted the theoretical prediction, and we could get very accurate values of the quantum defect, which I had mentioned before, and also the ionization frequency of the intermediate state. Now, I come to the main topic of our talk, which is Doppler-Enhanced Quantum Magnetometry with Rydberg atoms. So the background of this measurement was that when we were measuring the transition frequencies for the highly excited Rydberg state, so this is our setup. We have this probe laser, which is exciting from the ground state to the intermediate state. And this is our laser at 480 nanometer, which is the frequency doubled laser. And this is exciting from the intermediate to the highly excited Rydberg state. Now, here you can see the probe and the coupling laser are counter-propagating through the vapor cell where we have the atomic ensemble. And this is, of course, surrounded by mu metal, so that we don't want our measurements to be affected by ambient stray magnetic fields. So here, the probe and the coupling laser are counter-propagating so as to compensate for the Doppler shift as much as possible, because it's in the ladder system. But as we were doing this measurement, we found that there was an extra signal which was always coming. And then we tried to figure out why it was coming. And then we realized that because this coupling laser is very highly intense, so a part of the laser was getting back reflected from the glass cell. And this was making this coupling laser not only counter-propagating with the probe beam, but also there was another part which was co-propagating with the probe laser. And that's why we were getting an extra peak. So here you can see, we see this narrow Rydberg EIT peak, which is when the probe and the coupling laser is counter-propagating. But here we see a broader signal which comes from the co-propagating coupling beam with respect to the probe beam. So here we had yes. So here we can see that we have varied the detuning of this coupling laser, and here you can see how this relative positions of these two EIT peaks were varying with respect to each other. So to understand this better, what we did is we have put a magnetic field across the glass cell. So we deliberately put a co-propagating beam with respect to the probe laser, apart from the counter-propagating coupling laser. So here you can see that we have this probe laser going, and this coupling laser, one part is going counter-propagating to the probe laser and another is co-propagating. But to our surprise, we found that for the counter-propagating, for the co-propagating Rydberg EIT, the Zeeman splitting was an order of magnitude larger as compared to the Zeeman splitting in the conventionally used counter-propagating configuration. So this was a very surprising result, because generally Doppler effect is thought about something which is hindering precision measurements. So but the Doppler effect was actually resolving our Zeeman splitting of a Rydberg EIT signal much better than the conventional Rydberg EIT signal. So here you can see at higher fields we could get an order of magnitude larger Zeeman splitting using the co-propagating configuration. So we were quite perplexed by this result, and during a lunchtime discussion, one of our in-house theorists, Shobhan Datta, he got very interested in our results, and we started a collaboration for the theoretical modeling. So here you can see that this is our three-level system. So because of the magnetic field, there is Zeeman splitting of each of these levels. So you have in the ground state, there are a manifold, there are 5 Zeeman states. In the intermediate states, there are like 7 Zeeman states. And for the Rydberg state, it's very interesting, because the Rydberg state is so sensitive to magnetic field. Even a small magnetic field, mixes the hyperfine levels of the Rydberg state, and then there is a Paschen-Bach effect, and that's why it causes decoupling of the nuclear angular momentum and the total spin angular momentum. So here you can see that it's no longer the hyperfine quantum number, but here you can see we have the nuclear spin and the total angular momentum quantum number, which is acting independently because of the Paschen-Bach effect. So here you can see we have used the Lindblad master equation under Born-Markov approximation to do the theoretical modeling. And it turned out that this larger Zeeman splitting due to the magnetic field, it happens for the co-propagating configuration only when this condition is satisfied. That is, the Zeeman splitting of the intermediate state is either smaller or larger than both the ground and the Rydberg state and the Rydberg excited state. So here we can see that this is the zero temperature susceptibility, which is plotted here, and this is the thermal average susceptibility. So this is when we assume zero temperature, but here we have done a thermal averaging because our atoms are at room temperature at 300 Kelvin. So here we can see it reproduces the signal we had measured in our experiment. And here it's like the EIT window which we get when we vary the probe and the detuning of the coupling and the probe. So here also it shows the various conditions at which we get the Rydberg EIT signal for the co and the counter propagating configuration. So here, after the theoretical modeling, we see that the theoretical modeling exactly reproduces our experimental observation for the larger Zeeman splitting of the co-propagating Rydberg EIT signal. So here you can see, so this is the result for the zero magnetic field case, where you can see the theory is exactly matching with our experimental measurements as we change the coupling beam detuning. And so with the magnetic field, here you can see that the theoretical modeling is exactly matching with our experimental measurements, where we see a much larger Zeeman splitting for co-propagating configuration as compared to the counter-propagating one. So here you can see our experimental measurements and the theory, and they are in very good agreement. So here you can see that this very large Zeeman splitting, which for co-propagating configuration, which is exactly reproduced by our theoretical modeling. So this is for linear configuration of the probe and coupling beam, and this is for circular polarization for the probe and the coupling beam. And here also you can see that our theoretical modeling is matching very well with our experimental measurements. So we have also done further theoretical modeling, which is yet to be measured experimentally, where we have seen, played with the various polarizations of the probe and the coupling laser. Here you can see the probe is circularly polarized and the coupling is linearly polarized, where it's the other way around for these signals. And we have observed very interesting features in our theoretical results, and we hope to make the measurements to verify this very soon. So here you can see the probe and the coupling is both in the linear configuration, and here the probe and the coupling is one is pi polarized and the coupling is x polarized configuration. So here we can see very interesting features which we see in both in the counter propagating as well as the co-propagating cases. And so this we would like to measure in our experiments and hope to see this interesting features as well. So now I come to Rydberg excitation in cold, ultra cold atoms, which is the main focus of our Rydberg atom experiment. So here is the picture of our Rydberg atom experiment, where we have, here is the vacuum chamber where we realize the cold Rydberg atom cloud. Here we have the cold atom cloud at around 80 microkelvin temperature, and we further cool it to like 22 microkelvin temperature using subdoppler cooling. So here is our setup. So we have the cold atoms, which is realized here, and using what is called a magneto-optical trap. I'll not go in details here. So here we have two complementary detection systems. So we have a EM-CCD camera, which can measure the image of these cold atoms with very high spatial resolution. And we have here a single photon detector module, which can detect the photons from the cold atoms with very high timing resolution of around 5 nanoseconds. So we also have a provision for measuring the second order correlation function from the photons, which is coming out of the fluorescence from the cold atomic cloud. And so the electronics are developed in-house at RRI using what is called a real-time correlator for photon studies. So this is the schematic of our experimental setup. So we have this vacuum chamber where we have the cooling lasers from all sides, and we have a cold atomic cloud which is formed at the center of this vacuum chamber, which is called a magneto-optical trap. And here we have, as I had mentioned, two detection systems. And then we also shine this Rydberg laser, which is the laser which is coupling the intermediate state to the very highly excited Rydberg state. And this we use as a probe for detecting the cold atoms in the Rydberg state. So here I should mention that for the cooling laser has to be very highly intense. So because of this high intensity, this cooling laser is creating a Ortler-Town splitting of these levels of the intermediate state. So this is the signal which we get from the cold Rydberg atoms. So this is a Ortler-Town splitting signal which we get from Rydberg excitation of this cold atoms. So this is the first and presently the only cold Rydberg experiment in India. And so this is this opens up promising avenues for exploring various regimes of quantum technology with cold Rydberg atoms, which I'll explain in a few slides from now. So here's what is happening. So because of this very strong cooling laser, there's an Ortler-Town splitting of the intermediate state, and the Rydberg laser is actually used as a probe laser, which is probing this Ortler-Town splitting of this intermediate state. So here you can see this Ortler-Town splitting signal due to the cold Rydberg atoms. So another very interesting observation we have made in this Ortler-Town splitting with cold Rydberg atoms is that when we go to higher principal quantum number, for example, here you can see we have gone from 35 to 55. As we are increasing the principal quantum number, the interatomic interaction between the Rydberg atoms is increasing, and we see a broadening of this Ortler-Town splitting signal because of the increase in interaction, which causes a dephasing effect and creates a broadening of the signal as we go to higher principal quantum number. So we have also seen a very interesting effect that as we go to very high principal quantum number, like beyond 100, like 107 or 117, we see a complete distortion of this Ortler-Town splitting signal, which we have collaborated with Rajesh Nath of IISR Pune, and from the theoretical modeling, it turns out that this could be signatures of Rydberg blockade effect, which I had discussed a few slides back. So this we are going to submit to very soon. So at the moment, we are realizing optical dipole trap with for cold Rydberg atoms. And this optical dipole trap is a different kind of trap, which is different from magneto-optical trap, because there we use a near resonant light, but in optical dipole trap, we use light which is very, very far detuned from the atomic transition. So this makes very less heating and makes it a very conservative trap. So this is very highly desirable for trapping cold Rydberg atoms. So we are using a single beam optical dipole trap to trap this cold Rydberg atoms. And the idea is that we have a 1D optical dipole trap and trap this cold atoms and then excite them to the Rydberg state. So there has been a theoretical prediction that because of the Rydberg blockade effect, the Rydberg excitation will not be uniform, but there could be crystallization effect because of the Rydberg blockade. Because the Rydberg atoms, once excited, it prevents the surrounding atoms to be excited to the Rydberg state. So this could form crystallization due to the Rydberg blockade effect. And also at a higher and higher principal quantum number, we could measure the fraction of this Rydberg excitation and see how it varies as the principal quantum number, and we could measure the critical exponents for this kind of the dependence of the fraction of Rydberg excitation with the principal quantum number, which could be very useful input for the theoretical modeling. So since we want to address very highly excited Rydberg state, which has very small level spacing, so there we need to have the two exciting lasers locked to very high accuracy. So we generally this accuracy of these lasers, or the line width of lasers, are like 500 kilohertz. But to address Rydberg states at very high principal quantum number, we need to have very highly accurate and very stable laser systems which could address very highly excited Rydberg state. So that's why we are locking these two lasers to a hyphenous cavity. So here is the cavity which we are locking, and 2 days back we have successfully locked one of the lasers to this cavity, and we could get a very narrow line width of this laser, and we are in the process of locking this coupling laser also to this cavity. So the next step in our experiment is to have an optical tweezer to trap an individual Rydberg atom. So For that, we need to have an optical tweezer with very small focal spot, which is of the order of 1 micron. So this small focal spot will ensure that there's only 0 or 1 atom in the trap. If there are multiple atoms in this focal spot, then there will be inelastic collisions, which will ensure that both of the atoms will go out of the trap. So we have focused this optical tweezer to very small focal spot. And for that, we have placed very high numerical aperture lens inside the vacuum chamber to ensure that we have 1 micron focal spot for single atom trapping. So why is single atom trapping so interesting? Because the ability to trap single atom allows controlled engineering of the quantum state, and single quantum state is very important to encode and process quantum information at the quantum level, and it can enable us to explore quantum physics at the microscopic level. And so the importance of addressing individual quantum system is evident from the fact that the Nobel Prize in 2012 was awarded to Serge Haroche and David Weinland for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So this is our experimental setup for creating this optical tweezer, which is already in place in our experiment. And to ensure single atom trapping, we have already measured that our optical tweezer is giving sub-micron focal spot, so which makes it suitable for single atom trapping. So here you can see we have created an array of optical tweezer using what is called a spatial light modulator. So this is our optical schematic of the optical setup for this measurement. So here you can see that using a spatial light modulator, we can program it in according to our requirement for the experiment. We can make a multiple of optical tweezer. Here I'm showing in 1D, but we can do in 2D or any configuration of this array of optical tweezer. So I come to the future directions, what we are going to do in our experiment on quantum information and quantum sensing with cold Rydberg atoms. So the idea is to have individual atoms trapped in this array of optical tweezer, which I've shown you, and then excite them to the Rydberg state and create quantum entanglement using Rydberg blockade. So this is the setup, schematic of the setup for our experiment, where we use a spatial light modulator to create this array of optical tweezer, and we can also move this optical tweezers as with respect to each other using what is called a acousto-optic deflector, and we have high resolution imaging to image this individual atoms in the optical tweezer. And of course we have the detection system, and we also have a microwave signal generator to have measurement of electromagnetic fields in a wide range, starting from RF to microwave to even terahertz regime, to have Rydberg atoms as a very promising quantum sensor. So as we all know that in the microscopic regime, it follows single particle physics, and in a macroscopic regime, it generally follows many body physics. But what happens in the intermediate state, which is in the mesoscopic regime, so which is very interesting to study. So in our system, because of the giant nature of this Rydberg state, it's very promising to probe this very interesting mesoscopic regime, which characterizes the transition from the microscopic to the macroscopic regime. So we can do an atom by atom assembly to go from a microscopic regime to a mesoscopic regime, and then explore the scalability of the system to a very large scale to a macroscopic 2D array or a 1D array of individual Rydberg atoms. So because of the very strong long-range interaction between the Rydberg atoms, we can do quantum many-body physics and do quantum simulation of antiferromagnetic ordering using Rydberg atoms in a square or a triangular array. So this kind of system could be very promising for addressing open questions in quantum magnetism. So another new direction we would like to go in this experiment is to explore this long-range interaction in Rydberg atoms combined with disordered potentials. And so here we could explore new quantum phases in such kind of system, which is not very commonly explored. So as I had mentioned that Rydberg atoms has very high polarizability. That means extremely high sensitivity to electric fields, and hence it's so promising for quantum sensing and metrology. So the idea is to have individual Rydberg atoms in an optical tweezer, and then it can be a very accurate quantum sensor for microwave, terahertz or RF fields. It just depends on which energy levels we are choosing. So we can choose the energy levels such that it can be in the microwave regime or the terahertz regime or the RF regime. So this can act as a very versatile quantum sensor for a wide range of electromagnetic radiations. So we can also use quantum tricks such as squeeze states and probably overcome the standard quantum limit and probably reach the Heisenberg limit, which is the holy grail of quantum measurement. So this is our schematic of our optical setup. We already have this microwave signal generator for quantum sensing, and we are soon going to start with these experiments. So as I had mentioned, Rydberg atoms is a very versatile platform for exploring various regimes of quantum technology, right from quantum computing to quantum sensing and metrology to quantum simulation of many body physics. It can also do emulation of complex solid state systems. We can use it as a futuristic dipole antenna for observational astronomy, and also it can be used for ultra-fast quantum dynamics. So this is one of the very important slides where I'm showing the people who actually did this work, which I've discussed in this talk. So I have the PhD student, Shobhan, who is the lead author in the Doppler-Enhanced Quantum Magnetometry, and happy to say that he's going to submit his thesis next week. And Shilpa had done the Ortle-Town splitting in cold atoms, and presently she's doing her postdoc in Germany. And Yashika and Aishwarya are working on the quantum sensing and quantum computing project with Rydberg atoms. Venkat was one of the VSP students from IIT Kanpur who had worked also on the Doppler-Enhanced Quantum Magnetometry, and he's doing his PhD in Vienna. And Kirti is, she had done the measurement on the optical tweezer, and she's in ISRO at the moment. And we have theoretical collaborators, Shobhan Datta, who is from in-house theorist at RRI, and Rajesh Nath from ISR Pune. So I come to the summary of my talk. I discussed about our measurement on transition frequency of highly excited Rydberg atoms and Doppler-enhanced quantum magnetometry with Rydberg atoms. Then I talked about Rydberg excitation and Ortle-Town splitting in cold atoms due to Rydberg excitation. And then I talked about our future perspective on quantum information and quantum sensing with Rydberg atoms in an array of optical tweezer. Thanks for your kind attention.
Thank you very much for very nice result. So now session is open for questions or comment. Do you have any questions?
Hello. Thank you for a really nice talk. It's fantastic to see that you guys have doing a lot of experiments here. I want to have you explain a bit about the so the Rydberg atom is really good for the close interaction, right? Like nearest neighbor. But then what about the long range? It seems like a big problem for the Rydberg atom.
No, actually we have a complete control on the range of interaction because we can control at which principal quantum number we are exciting to, and that decides what is the range of the interaction of the Rydberg atom. So for example, at n equal to 100, you can have a range around more than 10 micron. So, and if you go even further, you can have even long range of the interaction. So it's
Okay.
completely controllable. So as I was saying, we can use this acoustic deflector here, yes, to make them closer or farther, this optical tweezer.
Oh, so you're basically using the tweezer
Yes.
to move them around.
Yes,
Okay.
yes,
So it's
yes.
not, so if it is in an array, and then I want like one of them on the side and connect to the other side, is that
Yes.
possible? Without like more like selective?
So it depends on which principal quantum number we are exciting to. So if it's a very highly excited principal quantum number and we have the tweezers within the range of Rydberg interaction,
Okay.
or what you can say Rydberg blockade radius. Rydberg blockade radius, that means in the range of interaction of this Rydberg atoms, then we can connect one atom to the other, no matter how many are there in
the
between.
middle. Okay, I see. Thank you very much.
Very nice talk. So this is probably more of a theory question, but when you were talking about that one-dimensional trap, or maybe it was two-dimensional trap, is there, so sorry, where you had the formula for the fraction of Rydberg excitations, yeah, bit there, yeah.
Yes.
So is there a fixed, I mean, yeah, as a function of dimension, is there something like a fixed interatomic distance which is assumed? What's the actual setting, for this result?
So since it's in a dipole trap, we can control the density of atoms in the dipole trap. So the density will decide how much is the interaction, or the, how much is the range of interaction. And as I said, we have a very good control, is that the principal quantum number to we are exciting. So that will decide what is the length scale of this. And of course we can change the temperature and the density and all the other parameters in the trap. So this can be completely controlled.
Okay, so I guess, but the formula gives a very specific
this one
answer. Yeah. So where is the density in that?
So
formula,
this
for
is
example?
completely different from here. I mean, this is
Oh.
a separate thing. So these are the things which we can do in this kind of thing. So this is different from, this is another measurement. It was proposed by our theory collaborator, which we plan to do in this setup.
Okay, so it doesn't correspond to the picture, or
well, I mean, this correspond to the fractions. So when we excite the atoms to the Rydberg state, we can measure the fraction. So it's basically for an ensemble of atoms, not here. So this is like a crystallization which we hope to see in this kind of system, but this is actually for the fraction of Rydberg excitation when we have an ensemble of atoms excited to the Rydberg state, and then we would like to measure this fraction and see how much is the fraction, and see what is the critical exponent which which will give rise to this relation. So we can compare our experimental measurements with this to get this theoretical exponent, which could be a good input to the theoretical model.
okay, thank you.
Any other questions? Okay, so if not, let's thank speaker again. So we enter lunch.